Okay, let's get started. I'd like to thank everyone who is joining us today. Welcome to today's CNCF webinar, Let's Untangle the Service Mesh. I'm Jerry Fallon. I'll be moderating today's webinar. We would like to welcome our presenter today, Dominik Tornow, Principal Engineer at Cisco. Just a few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. There is a Q&A box at the bottom of your screen. Please feel free to drop your questions in there and we'll get to as many as we can at the end. This is an official webinar of the CNCF and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of the Code of Conduct. Please be respectful of all of your fellow participants and presenters. Please also note that the recording and slides will be posted later today to the CNCF webinar page at cncf.io/webinars. With that, I'll hand it over to Dominik to kick off today's presentation.
Hey, thank you very much. And thank you everybody for joining Untangling the Service Mesh. I am Dominik Tornow. I work at the office of the CTO at Cisco Systems. And I focus on systems modeling to support the design, development, and the documentation of complex software systems. So first off, what is systems modeling and how is it different? Systems modeling is an analytical method. Traditional analytical methods divide and conquer. That is a process that is formally called analytical reduction. The system is decomposed into subsystems, and individual subsystems are examined individually. Systems modeling focuses on the system as a whole, not on individual parts. It is holistic. This webinar is all about the concepts behind service meshes. It's not about a feature set or how to use a specific service mesh. We are going to develop a holistic mental model. But what is a model? Or what is a mental model? A model is a collection of facts, so that every fact about the model is also a fact about the system. And a mental model is simply a collection of internalized facts. Mental models are the foundation of human reasoning. If you acquire a holistic mental model of a system, that will enable you to reason confidently about that system. So to kick off, let's revisit the traditional definition for a service mesh. A service mesh is a dedicated infrastructure layer for handling service-to-service communication. So this definition of a service mesh is in turn based on the definition of a dedicated infrastructure layer, as well as the definition of a service. Problem: there is no agreed upon definition, neither for infrastructure layer nor for service, which leaves the initial definition open to a wide range of interpretations. This definition will not spark the same understanding of the term service mesh in different readers, and certainly it will not spark a holistic understanding of the term service mesh. Next up, a service mesh is a set of user space proxies executing alongside your services and a set of management processes. Now, this definition is based on the presence of a user space proxy and the presence of management processes. In effect, this definition elevates an implementation detail to a defining criteria. Because according to this definition, any system that acts like a service mesh, that is any system that handles service-to-service communication, but that it is not implemented as a set of user space proxies and a set of management proxies, would in fact not be considered a service mesh. That seems to be an arbitrary criteria. So let's try this again. In part one, we will develop 3 distinct yet related mental models, each providing a foundation for the next. First, a mental model to reason about networking. Then a mental model to reason about services. And finally, a mental model to reason about service meshes. So first up, networking. In software engineering, a distributed system is an unbounded set of components from here on out called endpoints. Endpoints communicate by exchanging messages via a network. So according to this definition, networking is the very foundation of distributed systems. The behavior of a distributed system is attributed to the behavior of its endpoints and the communication between them. And fun fact, the complexity of a distributed system is attributed to the autonomy of its endpoints and the intricacy of the communication between them. So without loss of generality, let's focus this discussion on two endpoints, E1 and E2. An endpoint is connected to the network via an outbox to send messages and an inbox to receive messages. We keep track of the sequence of send events and receive events in an endpoint's history. If an endpoint wants to send a message, it will place that message in its outbox. Placing a message in its outbox is represented by a send event. The network picks up the message from the sending endpoint's outbox and determines the receiving endpoint's inbox. The network places a message in the receiving endpoint's inbox, and that is represented by a receive event. This can also be represented graphically as a time-space diagram. Each timeline represents an endpoint's history. Empty circles represent send events, and filled circles represent receive events. If necessary, we may also represent the network in the message exchange. A request-response pair, from here on out called a transaction, is represented as two messages, the request and the response, and four events, the send request event, receive request event, send response event, and the receive response event. And again, if necessary, we may also represent the network in the message exchange. Let's highlight two important aspects of networking: the global versus the local point of view, and addressing. First off, global versus local. So far, we have applied a global point of view. In this model, we are able to take the viewpoint of an all-knowing observer. We can observe both the inbox and outbox of E1 and E2 at the same time. But conversely, E1 or E2 cannot. We see the request appear in E1's outbox, and subsequently, we see the request appear in E2's inbox. Then we see the response appear in E2's outbox, and subsequently, we see the response appear in E1's inbox. So from a global point of view, we can follow the entire transaction at all times. But from a local point of view, we simply cannot. E1 can only observe its own inbox and its own outbox. It simply cannot reach beyond. So from the point of view of E1, E1 places a request in its outbox, and eventually a response appears in its inbox. The same is true for E2. E2 can only observe its own inbox and its own outbox. So from the point of view of E2, a request appears in its inbox, and eventually E2 places a response in its outbox. This is an absolutely fundamental realization. From the point of view of the all-knowing observer, E1 interacts with E2. In this example, E1 sends a request to E2, and in return, E2 sends a response to E1. But from the point of view of E1, it places a request in its outbox, and eventually a response appears in its inbox. And similarly, from the point of view of E2, a request appears in its inbox, and eventually it places a response in its outbox. From this point of view, neither E1 nor E2 interact directly with any other endpoints. It is this realization that lets us clearly define the concept of a service later on. But before we do so, let's visit addressing. So far, we have explored the fact that the network picks up a message from the sending endpoint's outbox and places a message in the receiving endpoint's inbox. However, we have not at all explored how the network determines the receiving endpoint. By far, the most common method is addressing. The network maintains an association between endpoints and addresses. Messages are tagged with target addresses. The network places the message in the outbox of the endpoint whose address matches the message target address. Sorry, inbox. So in effect, the network does not determine the receiving endpoint. The receiving endpoint is determined by the sending endpoint. This is referred to as smart endpoints, dumb pipes. At the moment the message is in the outbox, the eventual inbox is already determined. The network delivers the message, but does not inspect or interpret the message beyond the target address. So to summarize, we tend to reason about a distributed system from the viewpoint of the all-knowing observer, the global viewpoint. But we must not forget that the components of the distributed system cannot look beyond their inboxes and outboxes, the local point of view. And most commonly, networks determine the target endpoint of a message via addressing. In that case, the network is referred to as dumb pipes or sometimes a collection of dumb pipes. So equipped with a solid mental model about networking, let's look at services. Before we discuss the definition of a service, let's first develop an intuition of a service. When following this example, keep in mind, messages are load balanced. That is, a message may be processed by any process that constitutes a service. To develop an intuition, let's examine the example of a recommendation service. The contract of a recommendation service consists of only one operation. The get operation accepts a single ID and yields a list of IDs. An ID may be a movie ID, so the recommendation service may recommend other movies to watch. Or an ID may be a product ID, so the recommendation service may recommend other products to buy. But whatever the recommendation service actually recommends, the important aspect is the contract of the service. The service accepts a single ID as a request and yields a list of ID as a response. Now, how could we implement this service? Well, we could implement this service as a Python process or a Python container that connects to a database to retrieve recommendations specific to an ID. Here, let us assume the process is stateless and the database itself is both scalable and reliable. However, the connection to the database is not. So in this case, service and process are congruent. They're one and the same. But while this is functionally correct, this service is neither scalable nor reliable, since one process is neither scalable nor reliable. One process cannot withstand infinite load, and it cannot withstand a single failure. Since we assume the process is stateless and the database is both scalable and reliable, we may mitigate load and failure by redundancy. That is, we simply duplicate the recommendation process. In this case, the service consists of multiple processes. But we previously assumed the connection to the database is neither scalable nor reliable itself. So what can we do if the connection to the database fails? Well, we could deploy two different groups of recommendation processes. One, the primary group, returns the optimal recommendations in case the connection to the database is healthy. The other, the backup group, returns static recommendations in case the connection to the database is not healthy. So while the primary group retrieves recommendations from a sometimes available remote database, the secondary group retrieves recommendations from an always available local file. In this case, the service still consists of multiple processes, Yet not all processes are equal. We are dealing with two distinct groups of processes. But we are still missing a lot of machinery to make this work. So for layout reasons, we will not display the recommendation stores anymore. Yet please consider both the remote and local recommendation stores still present. So in order to mitigate load and failure, both process groups employ autoscaling. However, now the autoscalers themselves cannot withstand load and failure. Well, a situation we can once again address with redundancy. Now, in order to distribute requests among processes, we employ a load balancer. But since we are dealing with two different process groups, we need to employ a smart load balancer. For example, the load balancer may default a request to a process in the primary group, but if that process returns an error, retry the request to a process in the backup group. However, once again, now the load balancer itself cannot withstand load or failure. A situation we, once again, one-trick pony, address with redundancy. So now one service consists of a ton of processes, all with varying tasks and responsibilities that interact with each other in non-trivial ways. And this graphic looks much simpler, much cleaner than an actual system. This graphic implies a one-to-one relationship between parts of the system that may not exist. For example, some instances of an autoscaler may be responsible for more than one process group that constitutes a service. Or worse, some instances of an autoscaler may be responsible for more than one process group across different services. And all of that is true for the load balancers. So from the point of view, a service is an individual component, a component with identity and integrity. That is, identity and clear boundaries. Yet from another point of view, a service is an aggregate, a set of components with complex interactions. So fundamentally, there exists two different levels, a service level and a process level. The levels form a hierarchy with the service level above and the process level below. Levels are populated by components that characterize the level in question. So the service level is unsurprisingly composed of components that we call services. And the process level is composed of components that we call processes. The set of elements at the service level and the set of elements at the process level, they are disjunct, they do not overlap. Services are not processes and processes are not services. However, that is not to say that the service level and the process level do not relate to each other. On the contrary, the service level and the process level relate to each other in the most meaningful way. From a bottom-up point of view, a service is an emergent concept. Processes, the subsystems, and their interactions on the process level integrate into services, the supersystems on the service level. When subsystems integrate into supersystems, new characteristics emerge. These characteristics are in fact characteristic for the super level. They are irreducible. They do not trace back. They do not exist on the sublevel. For instance, in our example, the recommendation service was scalable and reliable. However, no individual process on the process level was scalable or reliable. So the whole is more than the sum of its parts. From a bottom-up point of view, from a top-down point of view, a service is a controlling concept. Services on a service level manifest as constraints on processes and their interactions on the process level. In turn, constraints on processes and their interactions on the process level yield characteristics that are meaningful on the service level. Since the service level imposes constraints on the process level, a valid point of view is that the service level is a control plane and the process level is the data plane of the overall system. And leaping forward to the topic of service meshes, another valid point of view is that a service mesh is a system that imposes constraints of the service level onto the process level. But now I'm getting ahead of myself. So in the previous subsection, we were developing an intuition, but we have been informally using the terms contract, service, and process. Let's have a look at a definition. When following this example, keep in mind that here messages are not load balanced. They are partitioned. That is, a message must be processed by a specific process that constitutes a service. So to develop the definition of a service, let's take a look at an example of a key value store. The contract of the key value store consists of two operations: a get operation that gets a value for a key, and a put operation that sets a value for a key. And here, keys are integers and values are strings. And the mechanics of the key value store are straightforward. Getting the value of a key that has not been set yet yields an empty string, and getting the value of a key that has been set to a value yields that value. No surprises. In order to discuss the concepts of contracts, services, and processes holistically, we need to discuss different points of views. The service to service or service level point of view, the process to process or process level point of view, the behavioral view, and finally the structural view. And furthermore, to make matters worse, we will subdivide the structural view into direct communication and indirect communication via a network. The term service itself is actually overloaded. Service may either refer to a contract or to a component providing that contract. So first, let us examine service as a contract. A contract is an agreement on the sequence of send and receive events on the service consumer's inbox and outbox. In the case of our key value store, the contract states that if a service consumer sends a put message via its outbox, it will eventually receive an OK, a confirmation, via its inbox. Then, if the service consumer sends a get message via its outbox, it will eventually receive the value via its inbox. Once again, from the local point of view of the service consumer, here the endpoint E, if E sends a put message, it will eventually receive an OK. Then, if the service consumer sends a get message, it will eventually receive the value. Next up, let's examine services not as contracts, but services as components that implement a contract. First, from a service to service point of view. From a structural direct communication point of view. This graphic shows a service consumer and a service provider, the key value store. From this point of view, we reason about the system in terms of services that communicate directly. We ignore the network. But let's add a twist. For our scenario, instead of one instance of a key value store, we have two instances of a key value store. And let's add another twist. We require that key value store 1 must be able to hold up to 1,000 keys, and key value store 2 must be able to hold up to 2,000 keys. Note that if we reason about the system as if its components communicate directly, addressing is not an issue. A message from the service consumer will simply find its target because it was put on the right channel in the first place. But now let's examine services as components from a service-to-service structural indirect communication point of view. From this point of view, we reason about the system still in terms of services, but now they communicate indirectly via a network. Here, a message from the service consumer will not simply find its target. The message itself must indicate the target, typically via an address. Here we agree that messages that are destined to key value store 1 must be addressed to a 1.local, and messages that are destined to key value store 2 must be addressed to 2.local. So in effect, a service is not just a contract or an instance of a component, it is also an addressing concept. Next, let's check out the service as components from a behavioral point of view. Let's have a closer look at the interaction of the service consumer and key value store 1. Here, the service consumer sends a put request to set key 0 to value A. Subsequently, the service consumer sends a put request to set key 1 to value B. Then, when the service consumer sends a get request, it will receive a response A. And finally, the service consumer sends another get request and it will receive the response B. Let's have a look at the interaction of the service consumer and key value store 2. Well, the interactions, the sequence of events are absolutely identical. But most notably, the sequence of events at the service consumer are identical and in line with the contract of the key value store. Now, let's leap over to the process-to-process model. First, let's implement the key value store process. Here, we implement the key value store as a Python application using the Flask HTTP framework, storing key value pairs in a local variable. If the process receives an HTTP GET request, the process yields the value for a key. And if the process receives an HTTP PUT request, the process sets a value for a key. But I added a little gotcha there. The process stores up to 1,000 keys. Reaching that threshold, the process will reject any more keys. So one process up to 1,000 keys. Now, from a process-to-process structural direct communication point of view, according to our requirements, we need two key value stores. Key value store 1 that can handle 1,000 keys and key value store 2 that can handle 2,000 keys. So since one process is able to store up to 1,000 keys, intuitively, we need 3 key value store processes that we may compose to get the desired results. One process constitutes key value store 1. 2 processes constitute key value store 2. But how will this composition actually look like? Well, for that, let's explore processes from a process-to-process structural indirect communication point of view. Again, 3 processes, again, composed. And again, now a message must indicate its target via an address. Notably, even though we are on a process-to-process level, we use a service address. So again, even on a process-to-process level, a service is an addressing concept. Next up, the behavioral point of view. Let's have a look at the interaction of the service consumer and key value store 1. Well, for key value store 1, the sequence of events on a process level is absolutely identical to the sequence of events on a service level. But let's have a look at the interaction of the service consumer and key value store 2. This looks very different. Both process 1 and process 2 are able to store up to 1,000 keys. So in order to store 2,000 keys in total, we need to partition the key space. Here, we will store the keys 0, 2, 4 and all even keys in process 1, and 1, 3, 5 and all odd keys in process 2. So when the service provider sends a put 0A message to set the key 0 to value A, that message has to be received at process 1. And when the service provider sends a put 1B message to set key 1 to value B, that message has to be received at process 2. So while on a service-to-service level, the sequence of events between the service provider and key value store 1 and the sequence of events between the service provider and key value store 2 are identical, on a process-to-process level, clearly they are different. However, they are still identical where it counts. The sequence of events at the service consumer are identical and in line with both the sequence of events on a service-to-service level, as well as the contract of the key value store. So to summarize, what is a service? First off, colloquially, sometimes we equate service with a pod, with a container, or generally services with processes. That is incorrect. Services are not processes and processes are not services. One valid definition of the term service is that service is a contract. Another valid yet competing definition of the term service is that a service is a component with identity and integrity that implements that contract. From a top-down point of view, a service controls the interaction of the processes that constitutes a service, so that the contract provided by the service is identical to the contract provided by the process set. So now we know what a service is, but we do not know how a service is actually implemented. That is, how are the constraints of the service level imposed on the process level? Now, this is where service meshes come in. Let's explore some options. For this example, please keep in mind again that messages are load balanced once again. That is, a message may be processed by any process that constitutes a service. Here we stay more general. We'll just assume the existence of some unspecified service S, and process 2 and process 6 constitute service S. Furthermore, we assume a dumb pipes network, where each process has an IP address, no trickery, no surprises. We won't always illustrate the IP addresses. We will instead simply use the alias process 1 and process 2 and so on. So if a process sends a message M with a target address of S, we want that message to be received either at process 2 or process 6. Well, of course, not both. So let's crawl towards service implementation. We do what we always do. We did this before. We load balance. But from a conceptual point of view, load balancing amounts to cheating. We do not address the message to a service. We address the message to a process, the load balancer. The load balancer is responsible for service resolution. That is, it examines the message and determines the target process. knowledge of a service does not exist in the network. Knowledge of the service exists in the endpoints. Process 3 needed to know to send the message to the load balancer if it intended to consume service S. And in turn, the load balancer needs to know to forward the message to either process 2 or process 6 if it intends to provide service S. So here the load balancer picks process 2. And in this case, we are all about smart endpoints and dumb pipes. The same is true for API gateways. Even though API gateways typically provide way more sophisticated service resolution, conceptually, load balancers and API gateways are identical. You're still talking smart endpoints, dumb pipes. Now let's walk towards a service implementation. Up to this point, smart endpoints, dumb pipes, knowledge of services existed in the endpoints, but not in the network. Well, if knowledge about services is scattered throughout endpoints, why not bundle that knowledge in a library? Now, when a process wants to send a message, it does not do so directly. It hands a message to a library first. Now, the knowledge about services is bundled in the library. The library, via its configuration, needs to know to forward the message to either process 2 or process 6 if it intends to provide the service S. So in effect, the library is a new edge of the network, but this network is different. This network is not a collection of dumb pipes. This network is a collection of smart pipes. The term smart pipes refers to a network with configurable or programmable service semantics. Generally speaking, about a network that knows about services. Well, now let's run towards a service implementation. Instead of bundling knowledge about services in a library, let's externalize that knowledge and put it in a proxy that executes alongside the processes. From here on out, everything is equivalent to the previous example. So in effect, now the proxy is the new edge of the network. And again, the network is a collection of smart pipes, a network with configurable or programmable service semantics. And indeed, a network that is a collection of smart pipes, a network that is configurable and programmable, a network that knows about services as first-class citizens is a service mesh. But how do you configure or program this configurable and programmable network, this service mesh, and what can it do? Well, the bad news, that depends. That depends on the implementation. But the good news, there is indeed a standard that covers the most prominent use cases, the service mesh interface. The service mesh interface defines how to specify traffic management, like for example, probabilistic traffic splits, how to specify traffic observability, like collecting metrics, and how to specify traffic policy, who is allowed to talk to whom. In effect, the service mesh interface defines a smart pipe configuration language, and it configures your proxy network accordingly. To learn more, check out SMIspec.io. So to summarize, whether implemented via a library or via a proxy, a service mesh is a collection of smart pipes, a network with configurable or programmable service semantics, a network that knows about services. So again, we got networks, and networks are split into dumb pipes and smart pipes. And smart pipes may be implemented with proxies or without proxies. Usually we think of service meshes as smart pipes implemented via proxies. But really, service meshes are just smart pipes in general. They are configurable and programmable networks. So in part 2, we will develop a mental model of Linkerd. But no worries, was a long ride, only 3 more slides to go. Linkerd is a proxy-based service mesh for Kubernetes and a cloud-native computing foundation incubation project. Linkerd is split into a control plane and a data plane who interact via the Linkerd gRPC protocol. The control plane corresponds closely to the service-to-service level. The control plane provides a user-facing API that enables the user to configure the network. That is, to enable the user to tell the network about the available services. For example, the user may configure probabilistic traffic splits, timeouts, or retries. The data plane corresponds closely to the process-to-process level. The data plane is proxy-based. Proxies execute alongside other containers in a pod. But proxies do not have to be added manually, but they are injected by a mutating admission controller automatically. The proxies communicate with the control plane via the gRPC protocol. They retrieve the service level configuration and translate that configuration to a process level configuration. In effect, the network of proxies enforce the constraints set by the service level configuration. The Linkerd control plane, and therefore the Linkerd gRPC protocol, are split into 2 main subsystems: the destination subsystem and the identity subsystem. The destination subsystem of Linkerd is responsible to determine the correct destination, that is, the correct pod for a message based on the user's service level configuration. And the identity subsystem is responsible to determine the correct MTLS certificates for the exchange. And in addition, the Linkerd control plane uses Prometheus to collect a wide array of metrics from the Linkerd data plane, more specifically from each Linkerd proxy. Note now, the following statements reflect my own opinion. They do not necessarily reflect the opinion of the Linkerd community, Buoyant, Cisco, or the CNCF. I'm also not affiliated with Linkerd or Buoyant beyond Cisco being a member of the CNCF as well. If you are interested in exploring or implementing service meshes, I highly recommend have a closer look at Linkerd. Linkerd is a concise implementation of a proxy-based service mesh on Kubernetes. Each component in the control plane, a Go application, and the data plane, the Linkerd proxy, a Rust application, is purpose-built for Linkerd. Therefore, there are no detours, there is no concept mapping, there is no translation. The code for both is straightforward to follow and straightforward to understand. As a starting point, I recommend to explore the Linkerd gRPC protocol. If you study the protocol in itself small and concise, you will get an instant idea about the concerns of the control plane, the concerns of the data plane, and how they interact. So if you want to get started on service meshes, give Linkerd a try. So for anyone who made it this far, thank you very much. And now I would like to hand it back and we open up for questions.
Okay, thank you very much, Dominik, for a wonderful presentation. We have a couple of questions here. How is the process not scalable in terms of K8s? We scale pods which run processes, and when it comes to service, it is the thing that exposes to the outer world. So we scale processes and not service anywhere.
So a single process, or in this case also a single pod, And let's assume for the example, it only has a single container. In itself, that process, that container, that pod is not scalable. It cannot handle infinite load. You need more processes, more containers, more pods. And it's also not reliable. Just one crash fault and that process, that container, that pod is gone. Now, it is on the service level that makes a set of pods and their interactions scalable and reliable. The scalability and reliability is an emergent concept. It emerges from a set of pods and their interactions and coordination, but not from an individual one. If you have, let's take an example, one individual Python process running on one machine, you cannot scale that beyond a certain limit, and it cannot withstand a single failure. One crash fault and the process is gone. However, if you apply redundancy, if you have more processes that all aggregate into a service, then you have scalability and reliability.
Okay. How do libraries make smart pipes? Won't it overload one particular process and not balance the messages?
I'm sorry, can you repeat that?
How do libraries make smart pipes? Won't it overload one particular process and not balance the messages?
So libraries make smart pipes only in effect, because your new inbox and outbox, so to say, is from the rest of your process that houses this library. The new inbox and outbox conceptually now is not with the network anymore. Conceptually, it is with that library. So you could argue the very same local viewpoint that the rest of the process now cannot look beyond the library. So the library is a new edge of the network. And the library itself, reading from configuration, or most likely being connected to a control plane, gets its information about the services. So one of the first libraries, and I think a precursor to Linkerd 1, if I'm not mistaken, is Finagle. So Finagle defined an entire network stack that had load balancing, but also other concerns like timeouts and retries, all bundled up, and to the rest of your application, it looked like the network. And if I'm not mistaken, also Google, with the recent release of Traffic Manager, has a scenario running where the control plane actually configures gRPC directly. So it configures a library instead of a set of proxies.
Okay. Is it a correct statement that Service Mesh is a highly abstracted implementation of the legacy remote procedure calls RPC?
I would tend to say yes. I did not think that through. In general, please, my email is on the screen. Do not hesitate to reach out to me if you want to discuss anything, but I have to pass on this question. Gut feeling, yes, but please do not quote me on it.
Okay. Unlimited to Linkerd. How are the steps to learn beginning from a simple API to Service Mesh in terms of fundamentals concepts?
So my journey started with Kubernetes services. So I would recommend that you check out Kubernetes services and understand or try to internalize, build a mental model of how Kubernetes services work and what they are. And I strongly recommend try to apply the viewpoint where you have two different hierarchical levels, a service-to-service communication and a process-to-process communication, and see how Kubernetes itself orchestrates the pods into services. And from there on, then it is actually a small step into the world of service meshes, because you can argue that the Kubernetes implementation is a non-configurable, non-programmable service mesh implementation. So if you now add configurability and programmability, you are actually again in service mesh land. So start with Kubernetes services and then make the leap into service meshes. And as I said, if you want to dig into the code a little bit, I recommend Linkerd as the individual components are purpose built. So they communicate clearly their purpose and their intent.
In terms of observability and telemetry, what elements does service mesh support?
Oh, that depends on the individual implementation of the service meshes, but generally they implement the golden metrics. So anything that happens on a request level, you are pretty well covered. But I would recommend, if you want to know about the observability, that you actually check out the observability capabilities of the individual meshes. I'm sorry, either me or you just cut out there.
Does it provide abstractions such as object request brokering?
No.
Okay.
But that's actually also a tricky question. If you want to discuss that further, as I said, please do reach out. Actually, I'm sorry, let me revisit that answer. So the service meshes that are most popular and that we also implicitly discussed here are service meshes that are all about HTTP requests. But you can imagine service meshes with any other L7, any other application level protocol. So from that point of view, you could argue that VTES is actually a service mesh that is able to speak the MySQL protocol and apply constraints on the communication between service consumers and multiple service providers. So any L7 protocol is potentially service meshable, but classically you think, at least of today, you think of service meshes as HTTP based. So I would still say no, but potentially yes.
As an architect, if I were to convince my client to use Linkerd versus Peggy, how should I go about it?
I'm sorry, Linkerd versus what?
API-G.
Actually, I do not know. I'm sorry, I cannot answer that question.
Can you tell us what the main differences are between Istio and Linkerd?
Also that I rather not. This is all. I'm sorry for interrupting. This would be wading very much into the territory of my own opinion. So I'd rather stay away from that.
Where did the virtual load balancing take place in Linkerd? Is it in a data plane itself or on the control plane?
Well, that depends on your point of view. So of course it has to happen on the data plane because it is the actual routing of messages in the sense of determining the receiving endpoint for a message. But of course, the control plane is involved in that. So it is information from the control plane that allows the proxy to examine a message, to determine what service that message is intended for, and then to determine what endpoint it may choose in order to fulfill this service. So I would always recommend not apply the analytical reduction or overly apply the analytical reduction, the divide and conquer. Try to see the interaction between the control plane and the data plane. And then you will see that most questions have an answer that lives both in the control plane and the data plane.
Okay, well, thank you very much, Dominik, for your time. That's all the time we have for today. As I said before, today's presentation and slides will be available later today on the CNCF website. Thank you again for your time, Dominik, and everyone, have a wonderful rest of your day.
Thank you for having me.